In today's lesson, we're looking at the primitives of sine squared x and cos squared x. Now, these integrals can be found using these substitutions, which we have already seen before in a previous lesson. Now, I've written here there's no need to memorize these results exactly, but it's handy if you know to look out for them, because when we see these, being able to make these substitutions is essential, really. Now, they are on the reference sheet, but they're on the reference sheet in a slightly different form. The reference sheet says sine squared nx, so that helps us even deal with a constant that's there, equals a half, and then they've used brackets here instead of expanding them out. So just a slightly different version, and it allows you to have an n there if you have one. So let's see it in action now. If we go to integrate something that looks like this, we need to start by just writing it in a different form. And then we can go ahead and integrate this one part at a time. So integrating 1/2 with respect to x just gives us a half x, or you could write x on 2. And then integrating this part, well, let's think about how we integrate cos 2x. Now, a couple of different methods here. You could keep this separate, and you could say, look, let's have a half cos 2x here, and we'll integrate that with respect to x. And then if you prefer that method of making the perfect question and adjusting for it, you might like this way. I'll show you a different method in a moment. Now, on our formula sheet, it says that if we have f dash x out the front, it makes it kind of perfect. So here, if we put what we want, and then think what we need to multiply by to adjust for it, something times 2 needs to equal a half. Well, this needs to be a quarter out here. And now I've written down my thinking over on the side here, but in actual fact, this wouldn't really be my thinking. This would just be my reference sheet. This is what's on the reference sheet, which helps me with this question. A perfect question has f dash x out the front, which we now have. We've got the 2, and so we can see that the result is the sine of f of x plus a constant there. So we have, for this part, we have the sine of 2x, and we need to have our minus a quarter hanging on out the front there. Like that, and then we add a constant, and we're done. Now, I mentioned that there's 2 ways always to do this, or maybe many more ways. Some people like to make this perfect question because then they can look at their reference sheet and say, look, I'm integrating that. There should be a dx there. And so I can see what the result is of this part. And then my fixed factor that's out the front just comes along for the right. Perfectly good method. Another thing that you can do is you can say at this point here, look, I know that when I integrate the half, I get a half x. And I know when I integrate cos 2x, just ignore the minus a half for a minute, what I'm going to get is the sine of 2x. So put in the part that you know, leave a nice empty space out the front there, and then you can just think through what needs to be there so that when you differentiate this term, you get that one. So let's differentiate this. The 2 would come out the front, and we'd get minus 2 there, and then we'd differentiate this and get cos 2x. Well, the cos 2x part is right, but we're wanting to have minus 2, and it needs to be minus a half. So to me, that's an obvious sort of marker to say, look, I need, when that 2 gets out there, I need to multiply by something to make half. And so the same thinking that I used to make my fixed factor, I can actually just put that fixed factor in straight away. And that way I don't have to make that separate integral. And it's maybe just simpler to think through that way. So whatever method gets you the right answer and sits right in your head, go for it. But you should get the same answer either way. Now, going into the second one, you'll notice that we've got a bit of an anomaly here. So let's think that through. If we actually look at our thinking on the side and just think, what do we know about the cos squared of x? Well, we know it's half plus a half cos 2x. Now look at the angles. This one's x, this one's twice as big. So here, if we've got half of x, then it just means that as we apply this formula, the angle that's in here needs to be twice as big, so it needs to be x. So again, our first step, we're not ready to integrate yet, so just rewrite the question as half plus a half cos, not 2x this time, but x. And again, I like that strategy of thinking over on the side and just making sure so that then what you put into your actual working makes sense to you. Okay, at this point, we could integrate as we go and put the result into our big brackets. Integrating the half, we get x on 2, or a half x, however you prefer to write it. And then thinking about what happens here, I know that when I integrate cos of x, I get sine of x. So write down the part you know, and then think, yeah, but what will happen when I differentiate that, I'll get cos x. I won't get my half out the front unless it's already there. It's a constant, so it can just come along for the ride. So this one's quite straightforward to do. Then we put our bounds in there too, 5 pi and 3 and 0. Next we sub in, 5 pi and 3 goes in where the x is. Now 5 pi and 3 halved makes 5 pi on 6 plus a half of sine 5 pi on 3. Now you might like to think through what that is and put the answer in straight away. I prefer to just make the substitutions because that way I've got my line of working, and on the next line I can sort of work out what each part is, and that way I'm not holding too much in my brain at one time. And I've got to subtract, bracket, the subbing in of 0. So I'm going to have 0 there plus a half of the sine of 0. Now I can see straight away that the sine of 0 is 0, so this whole part becomes worthless, it's nothing. So now here, the bit of thinking I need to do is, what is the sine of 5 pi on 3? Well, 5 pi on 3 is a lot like the sine of pi on 3, and pi on 3 is 60 degrees. And I know that the sine of 60 degrees is root 3 over 2. But this is going to be negative because 5 pi on 3 is not in the first quadrant, that's in the fourth quadrant, and sine's negative there. So I'm going to have my 5 pi on 6 here plus a half times negative root 3 on 2. And then on the next line I can tidy that up and say I've got 5 pi on 6 minus root 3 on 4. Now this whole thing is not asking for area, so I'm not going to put units squared. It's really just a definite integral, and I found the value of it exactly.